let us cover the topic dynamic RAM, DRAM, design. Let's start with the basics. DRAM is a type of memory commonly used in computers and other devices to store data. It relies on MOS-based capacitors and transistors for each memory cell, making it highly efficient in terms of capacity and cost. The use of these components also makes it easier to implement DRAM into devices. However, as we'll see, there are certain trade-offs to this design. Now, why do we call it dynamic? Unlike some other types of memory, DRAM requires constant refreshing of its stored data. This is because the capacitors that hold the data gradually lose their charge, which can cause the stored bits to flip, turning a 1 into a 0 or vice versa. To prevent data loss, an external refresh mechanism is used to periodically restore the charge in the capacitors. This need for refreshing is what gives DRAM its dynamic characteristic. The capacitor in a DRAM cell is called dynamic because it is not actively driven high or low by a direct connection to VDD or ground GND. Instead, the state of the capacitor, whether it holds a charge or not, represents the stored bit of data. This lack of active driving makes the capacitor node dynamic, requiring additional mechanisms to maintain its state. Data transfer in DRAM occurs in two distinct operations. During a read operation, the charge from the capacitor is transferred to the bit line, allowing the stored value to be detected. However, this process erases the original data stored in the capacitor, which we call a destructive read. During a write operation, data from the bit line is written to the capacitor, either charging or discharging it, thereby updating or restoring the bit value. Destructive read and refreshing. Because reads in DRAM are destructive, the data must be restored immediately after being read. Additionally, even if DRAM is not accessed, the charge on the capacitors leaks away over time. To prevent data loss, the contents must be periodically refreshed, which involves reading and rewriting every cell in the memory array. This refresh process occurs every few milliseconds, ensuring that data integrity is maintained. Let's look at some important features of DRAM. First, DRAM constantly needs refreshing, which is a unique requirement compared to other memory types. On the plus side, it is cheaper than SRAM, making it a cost-effective choice. However, it's also slower than SRAM in terms of speed. When it comes to power consumption, DRAM is more efficient than many types, but consumes more power than SRAM. Another advantage is its compact size, which allows it to be used in high-density configurations. The trade-off here is that DRAM has a short data lifetime, so refreshing is absolutely essential to maintain data integrity. DRAM was invented in 1966 by Robert Dennard at IBM. The fundamental storage cell of DRAM is built from two elements, a transistor and a capacitor. Together, they work to store and retrieve each bit of data. The transistor acts like a gate, while the capacitor stores the charge representing the bit, either a 1 or a 0. Here's how DRAM stores a bit. If the capacitor is charged, it represents a logic high or 1. If it's discharged, it represents a logic low or a 0. When data is stored, the transistor is activated by a word line connecting the capacitor to the bit line. Through this connection, the capacitor is either charged or discharged. The sense amplifier detects these tiny differences in charge to determine or modify the stored value. Reading and writing operations in DRAM rely on the word line and bit line working together. During a read operation, the transistor connects the capacitor to the bit line. The charge is measured by the sense amplifier, which outputs the corresponding logic level. However, this process drains the capacitor's charge, making DRAM reads destructive. To handle this, a process called precharging is performed. Precharging rewrites the read value back into the capacitor, ensuring that data isn't lost. Introduction to 4T DRAM. The 4-transistor DRAM or 4T DRAM is an advanced memory cell design. Compared to traditional 1T1CD RAM, it offers better performance and reliability. One of its standout features is the non-destructive read, which allows data to be read without altering or erasing it. This minimizes the need for immediate refresh cycles, making it more efficient. Structure and components. Each 4TD RAM cell consists of 4 transistors. M1, write transistor, handles the process of writing data to the storage node. M2, read transistor, enables data retrieval during read operations. M3 and M4, access transistors, control data flow in and out of the storage node. This structure improves control over the operations while ensuring data integrity during read and write processes. Data storage mechanism. Data in a 4-TD RAM cell is stored as charge at a storage node, typically represented by the capacitance of the transistors. Unlike traditional 1-T1-C DRAM, where reads are destructive, the voltage at the storage node in 4-TD RAM remains intact during reads. This key feature allows for non-destructive read operations, significantly reducing the frequency of refresh cycles. Operation phases. Let's break down the 4-TD RAM operations. Write operation. The bit line and word line are activated, turning on M1. Charge flows to the storage node, determining whether a S0 or 1 is stored. Read operation. Activating the word line turns on M to allowing the charge at the storage node to influence the bit line. Importantly, this read process preserves the stored data. Refresh operation. Even though reads are non-destructive, charge leakage still occurs over time. Periodic refreshes are needed to restore the original charge, ensuring long-term data integrity. 4TD RAM offers several advantages over other designs. Non-destructive reads. Unlike 1T1CD RAM, the data is preserved during read operations. Improved reliability. With multiple transistors, it is more stable against soft errors and manufacturing variations. Higher density. Compared to SRAM's 6-transistor design, 4-TD RAM achieves a good balance between functionality and silicon efficiency. 3-transistor DRAM cell, an innovative approach to dynamic memory design where each memory cell consists of 3 transistors. Unlike traditional DRAM designs, it enables non-destructive reads, meaning the data remains intact after being read. This design provides a middle ground between high-performance SRAM and traditional 1TD RAM, offering improved density and reliability. 3TD RAM cell bridges the gap between performance and density, offering non-destructive reads and compact memory arrays. While it faces challenges in retention time and design complexity, its advantages make it an attractive solution for high-reliability applications. Let's look at the structure. Each 3TD RAM cell has 3 transistors. M1 acts as the access transistor for writing data. M3 is the storage transistor, responsible for retaining the charge that represents a binary bit. M2 facilitates reading the stored data. The gate capacitance of M3 stores the charge, with a high charge representing a 1 and no charge representing a 0. This efficient use of the gate capacitance helps in compact storage. Now, how does the 3TD RAM cell store data? To write data. The write word line, WL write, activates M1. Data from the write bit line, BL write, is transferred to the storage node linked to M3. Depending on the data bit being written, A1 or a S0, M1 stores the corresponding charge at M3's gate capacitance. This completes the write process. Let's move to reading the stored data. For a read operation. The read word line, WL read, activates M2. If a 1 is stored, the charge at M3's gate turns it on, allowing BL read to discharge to a low level. If a S0 is stored, M3 remains off, and BL read retains its high voltage. This method ensures the stored data remains undisturbed during the read process, a major advantage over 1TD RAM. 3TD RAM offers several benefits. Non-destructive reads. Unlike 1 TB RAM, reading doesn't erase stored data, enhancing reliability. Higher density. It is more compact compared to SRAM, allowing for larger memory arrays. Improved performance. Additional transistors in the design provide stability and reduce the risk of data loss, making it ideal for critical applications. However, 3 TB RAM isn't without challenges. Limited retention time. Leakage currents can cause stored data to fade more quickly than in SRAM or 4T designs. Design complexity. Integrating 3 transistors per cell increases the circuit complexity, making it more challenging to scale for larger systems. Despite these challenges, the design remains a compelling option for applications prioritizing performance and density. Two-transistor DRAM cell is a design that balances simplicity and density. A 2TD RAM cell is a compact architecture designed for dynamic memory systems. With just 2 transistors per cell, it minimizes the area required for each memory cell while supporting essential read and write operations. The focus is on achieving a balance between simplicity and density, making it an efficient choice for certain applications. 2TD RAM cell is a simple yet efficient design, focusing on compactness and reduced power consumption. While it offers high density and cost-effectiveness, it has limitations, such as the need for refreshing and lack of advanced features. Despite these challenges, it remains a valuable option for memory applications where simplicity and density are key priorities. Let's delve into the structure of a 2TD RAM cell. Each cell comprises a storage transistor, which holds the charge that represents the stored data, an access transistor, which controls the read and write operations by connecting or isolating the storage node. The storage element is a capacitor connected to the gate of the storage transistor. A charge on this capacitor represents a logic high, or 1, while the absence of charge represents a logic low, or 0. This simple design allows for compact memory arrays. Now, how does a 2TD RAM cell write data? First, the access transistor is activated by applying a high voltage to its gate. This activation connects the bit line to the storage node. Data from the bit line is then written as a charge onto the capacitor. Depending on whether we are writing a 1 or a 0, the corresponding voltage is applied, ensuring the correct charge is stored. This process is efficient, allowing quick updates to the stored data. Reading data from a 2TD RAM cell involves these steps. The access transistor is activated, allowing the stored charge to influence the storage transistor. If the charge represents a 1, it turns on the storage transistor, enabling current flow through the bit line. A sense amplifier detects this current flow, confirming a logic high. If no charge is present, the storage transistor remains off, and no current flows through the bit line, indicating a logic low or 0. While simple, this method ensures the stored data can be accurately retrieved. 2TD RAM cells come with several advantages. Simplicity. With only 2 transistors, the design is straightforward and easier to manufacture. Higher density. The compact size allows more cells to fit on a chip, increasing overall memory capacity. Lower power consumption. Fewer transistors mean less power is used during operation, which is beneficial for power-sensitive applications. These features make the 2TD RAM cell an attractive option for cost-effective and dense memory solutions. Despite their advantages, 2TD RAM cells face some challenges. Limited functionality. Unlike more complex designs like 3TD RAM or SRAM, 2T cells lack features like non-destructive reads. Data retention issues. Leakage currents gradually deplete the stored charge, requiring periodic refreshing to maintain data integrity. Performance trade-offs. While the design is efficient, these trade-offs can affect performance in high-speed or critical applications. These challenges highlight the trade-offs involved in prioritizing simplicity and density. A 1TD RAM cell is the simplest form of dynamic memory design, using only 1 transistor and 1 capacitor per cell. Its simplicity allows for high-density storage, making it a key component in various electronic systems. While straightforward in design, its functionality supports essential memory operations. The 1TB RAM cell is a simple yet efficient memory architecture, offering high density and low power consumption. However, challenges like destructive reads and data retention require effective management to optimize its performance. It remains a foundational design in memory technology. Let's look at the structure. A 1TB RAM cell includes an access transistor that enables or disables access to the storage capacitor. A storage capacitor where data is stored as charge. The capacitor represents data as a logic high when charged and a logic low when discharged. However, due to leakage, this charge needs to be refreshed periodically. Writing data involves setting the bit line to the desired value high for a logic 1 or low for a logic 0. Activating the word line to turn on the access transistor. Charging the capacitor for a 1 or discharging it for a 0. This process is efficient and allows quick updates to stored data. Reading data involves activating the word line to turn on the access transistor. Sharing charge between the storage capacitor and the bit line, causing a slight voltage change. Detecting the change with a sense amplifier to determine whether the stored bit was 1 or 0. However, this process is destructive, meaning the stored charge is lost and must be refreshed immediately after reading. The 1TB RAM cell has several advantages. Its simplicity makes it cost-effective and easy to manufacture. Its high density allows for more memory cells on a chip, maximizing capacity. Fewer components lead to reduced power consumption, making it ideal for energy-efficient applications. Despite its advantages, the 1TB RAM cell faces challenges. Destructive reads mean data is lost and must be refreshed immediately after reading. Leakage currents gradually deplete the stored charge, requiring frequent refresh cycles. As cell sizes shrink with advancing technology, maintaining reliability and performance becomes more difficult due to increased leakage and scaling issues. One major challenge in DRAM design is that capacitors naturally leak charge over time. To ensure stored data isn't lost, DRAM relies on refreshing. The refresh process works similarly to reading, but instead of just detecting the charge, it immediately rewrites it to the capacitor. This need for periodic refresh is why DRAM is called dynamic. In contrast, SRAM or static RAM doesn't require refreshing because it uses a different mechanism to retain data. DRAM relies on capacitors to store data. Over time, these capacitors lose their charge, necessitating periodic refreshes to maintain data integrity. While refresh operations are critical, they introduce challenges in terms of energy consumption and system performance. Why is refreshing needed? DRAM cells are dynamic, meaning the capacitors holding the data gradually lose their charge over time due to leakage. Without periodic refreshing, the stored data would eventually be lost. Refreshing involves reading the existing data from the cells and immediately rewriting it to restore the capacitor's charge. This process is essential to maintain data integrity in DRAM systems. Refresh methods. Let's explore the different methods used for refreshing DRAM. Row refresh. In this method, the memory controller periodically selects entire rows of memory cells to refresh. The process involves reading the data in the row and rewriting it to recharge the capacitors. While effective, this method has a drawback. It can interrupt normal read and write operations, leading to increased latency. Self-refresh. DRAM can enter a self-refresh mode, particularly in low-power states, where it autonomously refreshes its contents without relying on the memory controller. This method is highly power-efficient and is commonly used in mobile devices to conserve energy while keeping data intact. Distributed refresh. Unlike row refresh, this technique spreads the refresh operations over time, refreshing only portions of the memory at a given moment. By doing so, it reduces the performance impact and ensures more efficient use of memory bandwidth, making it ideal for systems with high performance demands. Let's start with basic refresh techniques. RAS-only refresh refreshes one row at a time, requiring the controller to specify row addresses. CAS before RAS, similar to RAS-only, but allows for more efficient command management. Auto-refresh, this is an automated approach where internal counters handle row refresh, reducing the complexity for the controller. Advanced refresh techniques aim to mitigate performance and energy drawbacks. Hidden refresh enables simultaneous read or write operations during refresh, minimizing disruption. Retention-aware refresh adjusts the refresh rate based on how well each row retains charge. Charge-aware reduction skips refreshes for inactive or low-activity rows, significantly reducing overhead. Refresh operations can take a toll on system performance and energy consumption. They can account for up to 40% of total DRAM energy and cause performance degradation exceeding 30%. As DRAM density increases, the refresh overhead becomes even more pronounced, necessitating innovative solutions. Researchers have proposed several strategies to address these challenges. Refresh pausing introduces pauses to allow critical read-write operations, improving performance by around 7.2%. Granular refresh control adjusts intervals based on retention times, reducing energy usage by up to 80%. Charge-aware techniques analyze memory usage to skip unnecessary refreshes, achieving reductions of up to 83%. This table summarized the key refresh techniques, comparing their approaches and impacts. While basic techniques are reliable, advanced methods like retention-aware and charge-aware strategies offer significant efficiency gains, making them crucial for high-performance DRAM applications. Thanks. With this, we complete today's discussion on DRAM.